Okay, we're going to talk about a class of problems where the gradient vector is used to find tangent lines and planes. So this is yet another application of the gradient. So if you have a curve or a surface defined by equations such as f of xy equals 0 or f of x, y, z equals 0. And, for example, we could do x squared plus y squared minus 1 equals 0, or x squared plus y squared plus z squared minus 1 equals 0. These are my favorite examples. This is just a circle, obviously, and this is just that sphere. Then the gradient vector, and remember this is just fx, fy, or fx, fy, fz in the 3D case, and I'm using, again, my lazy notation f subscript x as the partial derivatives, then the gradient vector gives the normal vector. Okay? At each point, and it's normal to the tangent plane or the tangent line. So let me just give you some simple examples where you can just check this very quickly in your head. So if f of x, y equals y, and so then we take the level curves y equals 0, then if we just draw this, then this dark bolded line is y equals 0. Our normal vectors should simply point in the y direction. J is the normal vector at each point. So let's confirm that the gradient gives us the right answer. So the gradient is going to be fx, fy, and this will just be, of course, be 0, 1. So that's j. So we get the right answer for the normal vector. Let's let me just belabor this point in the 3D case. Fx, y, z equals z. If we take the level curve z equals 0, then the normal vector should simply point away from the xy plane, and it should just be k. So let's just confirm this. The gradient is fx, fy, fz, partial derivatives. So if we take the partial derivatives of z, we simply get 0, 0, and 1. This is, of course, k, the z unit vector. So we again get the correct normal vector by taking the gradient. So the same idea, it allows us to find the normal vectors of more complicated surfaces, and this gives us a lot more geometric information. I'll talk about some example problems you might see. So example problem 1 is if f of xy, now I'm going to do more complicated examples, xy, what you want to do now is find the gradient of f at 7, 3, and the tangent line to the level curve f equals 21. Remember, this is 7 times 3. At our point, 7 times 3. Remember, if you have a curve, you have to have a tangent line at a point. Okay? So the problem will also ask you to sketch the curve, the tangent line, and the normal vector. Or rather, we can just do the gradient vector. This is fun. The gradient will be in the normal direction too. So let me just underline the things that we're asked to do. We want the gradient, we want the tangent, and we want to sketch some stuff. So the sketching, I think, is the easiest part, and it actually gives us some valuable intuition. So the sketch, first, I want to sketch the level curve. So I'm going to sketch xy here, like so. So xy equals 21. Remember, that was what they told us to sketch. And so that is just y equals 21 over x. Now, do this qualitatively. Do not use graph paper or make this more complicated for yourself. So 21 over x, simply, you can just represent it like this. Okay, don't think about this too much. So 2, well, first I'm just going to put that point, 7, 3. So it will roughly correspond to this point here. All right, so now 3, I'm going to put the tangent line. And I'm just going to sketch it like so. Okay, so in particular, it has negative slope. Whatever we get, whatever number we should get, it should have negative slope. So this is a sanity check for when you're doing your work. And so finally, sketch the normal vector, the gradient vector. It'll point in the same direction. So the gradient vector, I'll just put this in dashed lines. And so I'll just label this the tangent. This is the curve, level curve. And then this will be the gradient or normal. Okay? So you can see the gradient should point into the first quadrant. So in other words, if it's a vector with a positive number and a positive number, that's what we should get. Okay, so now we've taken care of the sketch. So now let's do the gradient. So gradient f, it will be equal to fx, fy, which is yx. And then at our point 7, 3, we get 3, 7. So remember, this is plus plus as desired. Okay? And we only have one more thing to do, and now this is the tangent line. Okay, so how do you do the tangent line? So you have to, I would draw a diagram to remember the formula. The tangent line formula. So the tangent line formula is the normal vectors times the tangent vectors equals 0. Okay? And this is like if I just use this diagram right here. Here's a tangent vector. Clearly, it's going to be orthogonal to that normal vector. So that's the tangent line equation. And what diagram did I mean to draw? I meant, what is a tangent vector? So I'm going to draw this diagram. Here's the origin. Here's our tangent line. Here's R naught. And here is R. Okay, so now if I subtract these, I get this vector, which is a tangent vector. R minus R naught equals tangent vector. So draw this diagram. This is if you draw the diagram, you won't get too confused about the formula. So now I'm going to plug what I just got from my tangent vector into here. So n times r minus r naught equals 0. Okay? So now I'm going to use the gradient for my normal vector, because remember, it doesn't matter if it's rescaled badly, just divide it by both sides. 0 divided by some constant is still 0. So let me just avoid some more clutter. So our tangent line equation is gradient f times r minus r naught equals 0. And so our gradient, we had already shown this to be 3, 7. R is just x, y. And our r naught, I claim this is 7, 3. Why is it 7, 3? Because that's actually what they gave to us right here. Okay, so let me just unpack why it's 7, 3. If we have our level curve, and here's 7, 3, the tangent line hits 7, 3. That's the definition of that tangent line. Tangent line hits 7, 3. And so it's actually the base point of our tangent line. Right at 7, 3, the whole point of the tangent line is that it hits 7, 3. It hits the curve at 7, 3. It hits that curve. Okay, so let's plug it in. So 3, 7, and you take the dot product with x minus 7, y minus 3. So we get 3x minus 7 plus 7, y minus 3 equals 0. That is our tangent line equation. If you gave this, you would be done. So you could try checking if needed. Check the line. Check that the line looks okay. So you can just expand this and find the y-intercept form. So 3x minus 21 plus 7y minus 21 equals 0. This is 7y equals 42 minus 3x, otherwise known as y equals 6 minus 3/7 x. It has negative slope. That's what we wanted, because if we go back to our diagram, what we want is negative slope, because that's what the function is doing at that point. Okay? So now we're done. We have our 3 questions that we figured out. So let's do another example. So if g xy equals x squared plus y squared minus 6x, find the gradient of g at 1, 4, and use it to find the tangent line to the level curve g x y equals 11 at our point 1, 4. Remember, the at means at that point, tangent line at that point, and sketch all the stuff. So sketch the gradient, the curve, and the tangent. Okay, so I'm again just going to do the sketch first, just to, I think it's the easiest part. So you see an x squared plus y squared, right? So you know it has to be a circle. So to do that, what you're gonna do is you're gonna collect all the x's, and you're gonna write it as a sum of squares. So you need a sum of squares. So x squared minus 6x, this is x squared minus 2x times 3. So that 3, that's the critical piece. So what I'm going to do is I'm going to plus a 3 squared, and I'm going to subtract a 3 squared. So x minus 3 squared minus 9, that is x squared minus 6x. Therefore, g is x minus 3 squared plus y squared. That's our sum of squares. Minus 9. So that's clearly a circle of, I'm sorry. So now our level curve, it sets this g equal to 11. So it's the circle of radius square root of 20, center at 3, 0. So we can draw this thing pretty easily. So here's 3, 0. And to see how big the radius is, just note this is the square root of 4 times 5. This is 2 square root of 5. And just as an estimation, this is around 4. Something bigger than 4. So you know the radius will hit somewhere out here. Again, always qualitative, never quantitative. Okay, so here's the level curve. g equals 11. So now what we do is we draw the tangent at 1, 4. So here's 1, and here's 4, roughly speaking. Again, this is all qualitative. Now I'm just going to draw a tangent line here. Doesn't have to be pretty. This certainly isn't. And I'll just label this the tangent line. And finally, I want that normal vector. So in particular, you have a negative and a positive in our vector components. So that's what we should be getting when we take that gradient. All right, so now let's do the math. So we want the gradient and the tangent line, just to rephrase. So g, remember, it was x squared plus y squared minus 6x. So if I take the gradient, this is fx, or I'm sorry, gx, gy. So we get 2x minus 6, and then 2y. So then at our point 1, 4, we just get 2 minus 6, so negative 4. And then we get 2y, so 8. Okay? So that's our gradient. So in particular, we have a negative and a positive that agrees with our picture. That's what the gradient should be doing. Okay? So now what we want is the tangent line. Again, draw the diagram. I would draw it because it is kind of hard to remember that formula otherwise. So here's our line, and here's the origin. So what I do is I draw two vectors. And then I subtract. So then now this thing is a tangent vector. So now this is, if I call this r, and I call this r naught, then this is just r minus r naught. So this is a tangent vector. Okay? And r lives in the line. So the tangent line equation is that the normal vectors times the tangent vectors are 0. They are orthogonal. Okay? So that means you plug this in. The gradient, remember the gradient is normal to the curve at that point, and then times the tangent vectors r minus r0, this gives you 0. So let's just now plug this in. So minus 4, 8 times x minus something, y minus something equals 0. And our somethings is just 1, 4. Again, 1, 4 is the base point of the tangent line. If we go back to our diagram, this here is 1, 4. It's where the tangent line hits the curve. So let's just expand this. We get negative 4 times x minus 1 plus 8 times y minus 4 equals 0. That is our tangent line equation. Okay? And we can just expand that. Just if we want to double check. This isn't needed, but just in case you want to check your work, this is negative 4x. Let's see, this is plus 4 plus 8y minus 32 equals 0. So it looks like 8y equals 30. Let's see, this is 28, I guess. 28 plus 4x. So in particular, it is positive slope. And is this right? Well, we go back to our graph. We see the slope is positive. So it's highly likely we did our calculation correctly. Okay? So I won't belabor you with another one of these examples. What I want to do now is just talk really quickly about a 2D example, or rather a 3D example. So a final example I just want to consider is when is a point on the paraboloid y equals x squared plus z squared, don't worry, this is not going to be a long example, is tangent, oh, I'm sorry, when is a point, at which point, I'm sorry, at which point on the paraboloid is the tangent plane parallel to the plane defined by 7x plus 2y plus 5z equals 4. Okay, so if I just go back to the 2D case, and we just have some parabola, and we have some plane, then we want the tangent line to be parallel to that line. Okay, so this is another way of saying this, though, is that you can just ask for the gradient vectors to be parallel. So parallel gradient vectors. So this is an equivalent way to do that. So first I need to write in f equals 0 form. Okay, so for the first one, I'm just going to do x squared plus x squared plus z squared minus y equals 0. And just to call this some f thing, I'm just going to call this f. F of x, y, z equals 0. Okay? Now, we also have our plane. Our plane is 7x plus 2y plus 5z minus 4 equals 0. If I put it in f equals 0 form, and I'm just going to call this p for plane. Okay, so now we take the gradients. Gradient f is fx, fy, fz. So this is just 2x, negative 1, 2z. Gradient p, the gradient of that plane, that's 7, 2, 5. Okay, so now 3, we just need the parallel. Remember, we need the gradients to be parallel in order for the tangent lines to be parallel. This is really planes, but it's the same idea. So the parallel condition, another way of saying this is that the cross product of these two things is 0, right? Because the cross product tells you how orthogonal two vectors are. So let's just do the cross product. It's pretty quick. If we go back to our vectors, looks like we put 2x, negative 1, 2z, and we can put 7, 2, 5. Is it? Yeah, it's just 7, 2, 5. Okay, so now we take the determinant. So this will be I times negative 1, 2, 2z, 5, minus j. Remember, you need that minus sign. Although in this case it's 0, so we actually, you can make that mistake if you want to, but only this time. So 2x, 7, 2z, 5, plus k times 2x, negative 1, 7, 2. So just to reiterate, I was doing these columns to do this determinant. Okay? You remember, you exclude the columns. You exclude the column that I comes from. So if I was doing the I would only look for the other two columns and the row. So let's just do these rest of the determinants. This is I times negative 5 minus 4z. This is minus j times 10x minus 14z plus k times 4x plus 7. All of these things to be parallel. 0 plus 0 plus 0. So we end up with 3 equations. Negative 5 minus 4z equals 0. 10x minus 14z equals 0. 4x plus 7 equals 0. So the first one is easy. X equals negative 7 over 4. And the second one is easy too. I'm sorry, the first one. z equals negative 5 over 4. So now, in order to check a solution exists, we just need that third one to make sense. So 10 times negative 7 fourths minus 14 times negative 5 fourths. Let me just check to see if this works. This is, I hope you don't mind if I get rid of these 4s, because we're trying to check if it's 0. So negative 70, let's see, plus 5 times 14, I believe that is 70. So this is negative 70 plus 70. This is 0. That is what we want. We get 0. So, by the way, this remaining equation, if it's not 0, no solution. But we were lucky this time. There was a solution. So therefore, our point x, y, z equals, let's see what we get. We got negative 7 over 4. And we need our y. And then our z is, what was it? It was negative 5 over 4. This is the desired point. We need our y, but luckily it's on the paraboloid. Remember? It's the point on the paraboloid parallel to that line. So the paraboloid was y equals x squared plus z squared. Just plug it in. So negative 7 over 4 plus 5 over 4 all squared. This will give me 49 plus 25 over 4. I believe this is 74 over 4. So this looks like 37 over 2. So I'll put 37 over 2 here. This is the desired point we were looking for. Okay. I won't take up more of your time. Thanks for watching.